Of college prep physics. This lesson is on something called the normal force. And in a way, normal is kind of abnormal because it's not real. It's a made-up force that some physicist figured out to help us basically explain why we don't fall through the floor. However, I did tell you before why we don't fall through the floor. The reason is there's repulsion between the electrons in the floor and electrons in your feet. There's also the fan blade idea, right? So that's really why we don't fall through the floor, but that's hard to calculate, and it doesn't help an engineer very much. As an engineer, you want to be able to design something. You need to be able to sort of give a number and an easy explanation to the force of contact, the force pushing up on something that's resting on the floor. Okay, and that's what normal force is. Yeah, so I told you this already, so move on. So what I mean is this. So we've talked about system diagrams, free body diagrams, all that, and that's what we're looking at here. Imagine you've got Batman, and he's got his a weight. His weight is the force of gravity acting on Batman is 1,500 newtons. Well, if he's just standing there on the floor, right? There's got to be an equal and opposite force, otherwise he'd be falling down. If the only force acting on Batman was gravity, he'd be moving down right now, right? However, that's not true. The forces are balanced, and that's what we call the normal force. So it's the name we give to the, everything, electrostatic repulsion and all that, fan blade concept, the whole thing. It's the name we give that to explain. And it's got to be exactly equal to his weight, because Batman's standing there. He's not going anywhere. Now, normal force is also, if you were going to lean on the wall, sort of sideways and on the wall, it'd be the force pushing out on you. It's always perpendicular to the surface, pushing you away from the wall. Okay? We usually calculate it between your feet and the floor, and usually the idea is that you're resting on the floor, you're not moving up or down, so that normal force is actually really, it's pretty easy to calculate. Wait till we do the elevator when you do move up and down, and we'll talk about normal force and scale, but we're just going to talk about that in class, not on a video. So, like I say, it's a balancing force. If an object's resting on a surface, the normal force is equal to the force being pressed down. Most often, it's equal to gravity, but sometimes there's another force involved, so you can't always just say it's equal to gravity, and I'll show you some examples. So in these examples that we're doing, I'm just assuming I'm doing completely generic. We're saying you have an object. This is a free body diagram, so it's not a ball. It's just that free body diagram just is the representation of my 1 kilogram textbook. Okay, so imagine I have a textbook, 1 kilogram, sitting on a table, and I want to figure out both the normal force and the gravity force. Okay, well, first and foremost, they're going to be equal to each other because I'm resting. The thing is resting. It's not moving. So if something's resting, the forces must be balanced. So here's the solution. First, you find the gravity force, and it's mass times 9.8, like I told you in the last note. So 1 times 9.8. So the force of gravity acting on this 1 kilogram, I'm calling it a textbook, okay, is going to be 9.8. And since there's no other forces involved, and this textbook or whatever is just resting, it's not moving up or down, that means up force equals down force, so normal force must be equal to, but opposite direction, as gravity. Okay? So 9.8. In the second example, I have another force, and so what this could be, and we'll talk about this in class, but this could be, for example, on, say, your desk. 5 kilograms might be an okay number for your desk. Maybe, whatever, say your desk. And your desk is resting on the ground. However, you're sort of pulling it up just a little bit. You're not lifting it off the ground, but you're sort of applying a bit of an upward force without lifting it. And that would be the FA, 10 newtons. You're pulling it up with 10 newtons. You're lightening the load, the pressure between it and the floor, but you're not lifting it. So there's still a normal force. Because only normal force, there has to be surfaces in contact. If the surfaces weren't in contact, there'd be no normal. And the question is, what's gravity force on this 5 kilogram object? And second, what's the normal force? So to find gravity, always the same, mass times 9.8, that never changes. So you get 49 newtons. To find normal, you have to say, okay, well, my up forces, these two, have to add up to the down force. This is some object resting. So the normal, Fn, that's a symbol for normal, plus applied force is going to equal the 49 newtons. So 10 plus normal has to equal 49, which means normal is going to be 39 newtons. So you have 39 here, 10 here, that equals 49, which equals gravity. Okay? A couple more examples. Never mind that, just scratch that out if it's not scratched out already. This time we want to find the normal force. We know our gravity force. We have this applied force of 100, and this is as easy as it looks. These two have to add up to gravity, so Fn must be 100. Okay? These two add up to gravity. Up equals down. Fn equals 100. 100 plus 100 equals 200. Okay? I think this is the last example. This time I decided to say, okay, let's say this thing is actually moving up. It's a uniform motion, so that means that the velocity is not changing. First find the net force and then find the normal force, because that could affect the whole process. Okay? And we have some force. What this could mean, this one I think is easier to explain. Imagine you're talking about, say, your desk again, a heavier desk, and it's sitting on the ground, and you push down on it. You're sort of resting and you're pushing, applying some force downward on it. That might be an example of what's going on here. Okay? Meanwhile, the thing is moving up because you're in an elevator? I don't know. I don't have a very good imagination. I am good at math though. So what this means is the net force. So first thing is this. If uniform motion, then acceleration is 0, so net force. And so net force is 0. Okay? And so I just threw this in here to say that usually things aren't moving up or down, and on your tests and that they won't be, but they could be. And for example, we're going to have this great, you do this one lab, everyone does this one, and it's the elevator lab, and of course in an elevator you're moving up or down. So you could be moving. Okay? So we know the normal force, we know the net force is 0. So even though the net force, it's moving, if the net force is 0, the forces are still balanced on this. Sorry about this. Come back. These forces are balanced, meaning these two are still going to equal the normal. Up equals down. Even if you're moving, because you're not accelerating. Acceleration changes everything, and we're not going to do any with that. So then you just say, okay, my normal has to be equal to the sum of these two, so my normal is going to be 250. Okay? And so the last thing I wanted to say about normal force is getting a feel, and I sort of hinted at this. It's not theoretically correct, it's not physics terms correct to say that normal force and pressure are the same thing. However, I think of that as an easy way to, you think about pressure between the surfaces. If they're really squeezed tight together, there's a lot of pressure. That means there's a lot of normal force. If they're really light, like barely touching, then there's not very much normal force. So, say you got your desk sitting on the ground and you attach a couple helium balloons and they're applying a little bit of force up, but not enough to lift it up. So it's sitting there, but the load is lightened. You have less normal force than if you took the balloons off and sat your rear end down on the desk, because then you're creating more pressure between the desk feet and the floor. Excuse me. So normal force that's how you can picture it. Theoretically not correct, because force is a different story, or pressure is a different story. We'll talk about that later in the course, but that's how you can picture it. So let's just say, so if your desk had a weight of 150 and you push down on the desk, then the normal force would be bigger than 150 because there's more pressure between the surfaces. If you pulled up on your desk without lifting it, the normal force would be less than 150 because like the helium balloons is what I'm thinking, right? They're just pulling up a bit but not enough to lift it. Well, they will decrease the pressure between the desk feet and the floor. And if you didn't touch your desk at all, it's just sitting there, there's no balloons, there's nothing attached to it, no textbooks on it, then the normal force will be equal to its weight, which would be 150. And that's it for this lesson. And we do have a next class, or maybe later in this class, we'll spend some time on the elevator talking a bit more about normal force.